Good morning, everyone. I'm Kyung-bok Jung from Korea Gas Corporation. So today I'm here to introduce you about the hydrogen distribution market and the works we do in Korea Gas Corporation, and thank you so much for giving me this opportunity to explain this today. So today I'm going to cover the status of the hydrogen market in Korea and abroad, and also major tasks that we are working on, and also the prospect and the outlook of the hydrogen distribution market in Korea. Since the Paris Agreement on Climate Change, as of January 1st this year, actually, this agreement took effect. So we committed to limit global warming to well below 2 degrees Celsius. So we try to achieve a net zero target. So this is a global trend to achieve this target toward the decarbonization. So since then, there has been a lot of policies have been introduced regarding hydrogen, especially in the United States. As of 2030, 1.2 million hydrogen cars and 300,000 logistic trucks. So they try to achieve a green parity. And also, if you look at EU and Germany, they also try to expand their production facilities for green hydrogen based on renewable energy and water electrolysis. And if you look at EU, they try to increase to 40 gigawatt by 2030. And also Canada will expand the energy, hydrogen demand and supply. Also, they try to increase the share of hydrogen in total energy consumption to 30%. Also, and Japan try to produce 800,000 hydrogen cars and 1,200 hydrogen buses. So as alternative energy, the value of hydrogen is increasing. So these are the Korean policies for hydrogen market. From 2019, so the roadmap was set out to support the hydrogen economy, and based on this roadmap, specific plans and goals were set out. So in July the 3rd, Energy Basic Plan was set up, and as of 2020, an Hydrogen Act was enacted. And as of February 5th, actually, it took effect. So as of February 5th, 2021, as Hydrogen Act took effect, so our agency was established. So we are going to run the hydrogen exchange market. Also, we will maintain a certain appropriate level or price level for hydrogen. So we'll oversee the hydrogen distribution market. So this is the goal, and so we are carrying out these activities based on the Hydrogen Act. Promotion, so hydrogen promotion, distribution, and safety. So we have 3 dedicated agencies to cover promotion, distribution, and safety. So our center actually carried out group buying, hydrogen group buying in May. So we also plan a second round of group buying. So let me explain further about the hydrogen policies in Korea. According to the 3rd Energy Base Plan, renewable energy, LNG, and hydrogen, we try to expand the role of these renewable energies. And also hydrogen will be more utilized for a transportation fuel as well as power. So this goal is captured in Energy Base Plan. And the NDC target was set as of August 2021. Carbon Neutrality Act is legislated. So we try to reduce. We are supposed to reduce emissions by 30% The target was initially 24% for reduction, but this year, as we have a new carbon law, so target was strengthened to reduce by 35%. So if you look at the news, actually, the government is pushing forward 45% reduction. So let's take a look at the hydrogen distribution structure. After these hydrogens are produced, and then they will go to the distributions, and then they'll be carried by tube trailer, and then they will deliver to charging stations. We have about 600 tube trailers in Korea. And also the length of the pipeline is about 280 kilometers. And the supply and demand as of 2020. So we did an investigation for hydrogen throughout the whole life cycle. So I think this is for the first time ever that we investigated the status of hydrogen working together with the private sector. The production volume is about 1.84 million ton. Among them, byproduct is 1.2 million, and reforming hydrogen is 720,000 ton. So mostly they are self-consumed for petrochemical and steel industries. They are using these hydrogens on site. And so tube trailers are used to transport hydrogen. And also, if you look at the hydrogen utilization, so the hydrogen for transport is 1,393 tons as of last year. So if you look at the total production, it's about 0.09%. So let me share what we are doing in this area. So we try to establish a hydrogen exchange. And the target is to have this up and running by 2023. So as we prepare for the platform, trading platform, we try to stabilize pricing. Also, we try to pursue group buying so that we can maximize bargaining power, so that we can supply hydrogens at more affordable price. So this approach is actually composed of two steps. One is a group buying, and the other is a direct individual purchasing. So direct transaction with the charging operators. So we currently is actually developing electronic platform. So the plan is to have this platform up and running in 2023. And next is group buying. So we try to stabilize a hydrogen price through competition. Early this year, we had a first group buying in May 2021. So private charging stations took part in this process. So we are going to introduce competition process. Actually, we selected suppliers, and we were able to reduce unit price by 11% from 7,328 won per kilogram. So at the end of November and early December, we are going to run a second group buying. So next is a demand and supply policy. As we utilize byproduct hydrogen, so we try to get the price competitiveness so that we can drive the demand So we have a byproduct hydrogen as well as extraction hydrogen, and in mid and long term, so we will, when we consider the trend of the hydrogen's relative prices, I believe they will be able to supply more low carbon hydrogens. And high pressure tube trailers and liquefaction and pipeline transportation, we will be able to reduce the distribution. Also, utilizing CCUS, will be able to tap into blue hydrogens, and in a long term, we will use green hydrogen. So we consider a water electrolysis and a water pressure hydrogen distribution. So if you look at the plan specifically, so throughout the life cycle, so from the production volume to consumption volume, we investigated actually. We studied this. In 2022, for hydrogen transportation, so we studied the volume. It's about 10,000 ton for transportation. And the demand is about 6,000 ton. So there's no issue in securing the demand. So we are going to build a demand forecast model so that we'll be able to address and deal with the demand going forward. Next is to establish a order or the market, distribution market, and culture in hydrogen market. So you can see what is banned and what are the penalties and fines under the Hydrogen Act. So based on this Hydrogen Act, we actually investigate this regularly. And so hydrogen charging stations and charging amount and sales amount, also the pricing at charging stations, and also the vehicle waiting in charging stations. So you can check those informations using application. This application is called KHIA. So it is actually under test right now. And if you go to a Google store, and you can find this app KHIA, and if you utilize this application, this is a GPS-based application. So you can find nearest charging stations. And also you can get charging price informations, and also whether you can charge it, charging station availability can be also checked on this web application. So we are going to provide this service to the public continuously. So let me share the outlook for a domestic hydrogen market, distribution market. So we expect that the demand as well as consumption amount will increase steadily around 2050. You can see there's a huge gap between the consumption and supply. And actually, the demand will exceed the supply by 2030 because we overachieved our NDC. So there is a chance that the demand may exceed supply. So even though I said earlier that in 2032, actually the demand will exceed supply, but we believe that this can be further expedited depending on situations in the market. So if we separate them to gas, liquid, and chemical, tube trailer is the only sole distribution channel, and so the technology is ready. But the problem is that the investment cost is pretty high. It costs about 200 million won per unit per tube trailer. Also, it cannot carry large amount. So the market is a little bit reluctant to make investment in tube trailers. And if you look at pipelines, in the future, yes, we need pipelines for power generation. So the advantage of pipelines are it can carry large volume and also it can carry large volume stably. So, but if you look at liquid and liquidified technology, it will take some time to actually fully develop technologies, but it's easier. It will make the green hydrogen distribution easier. And the next one is chemicals, LOHC, ammonia. So maybe this is feeding a process to import large volume of hydrogens from overseas. But as the technology advances, we will be able to reduce the operation costs. So depending on the technology readiness, probably the cost of operation will be determined. So let me summarize. So we have in the short term, we have a distribution center. So we are going to utilize tube trailers, and we can expand the expansion of these distribution channels. And in the mid and long term, we will import hydrogens from overseas. Also, we can also introduce pipelines so that we can make distribution channel more effective and efficient so that we can reduce the distribution cost. So in a long term, to stabilize hydrogen economy, we need to lay diverse infrastructures. And if you look at here, hydrogen import, liquefaction hydrogen need to be imported and supplied in Korea. And also expanding hydrogen pipelines. And so when we reach this level, then we'll be able to we'll be able to efficiently supply hydrogen to the people. And with that, let me conclude my presentation. Thank you so much for listening.
네.
Thank you for the great presentation. Please give him a big round of applause. Now we'd like to invite the second speaker. He's going to talk about the development of the trend of the automation technology for the safety in hydrogen society. Please welcome Mr. Lee Jong-won, Senior Business Manager from Emerson Automation Solutions. Hello, ladies and gentlemen. I'm Lee Jong-won, in charge of the overall sales. Today I'm going to talk about the development of the trend of the automation technology for the safety in hydrogen society for about 20 minutes. So if you have any questions, you can ask me in the panel discussion time. First of all, let me briefly introduce Emerson. We established in 1890, so we are over 100 years old. And we hire more than 80,000 employees around the world. As of last year, our revenue reaches more than $16.8 billion. And regarding the software annual sales from software portfolio, we have more than $2 billion. So we are very strong in software and focusing on digital automation transformation system. These are our specialty. So let me introduce about Emerson Korea. So it was established in 1988. 32 years ago, we hired more than 600 employees. And we have more than 200 project engineers. And they are serving the customers with our solutions. As you can see in the slide, you will see production, assembly, and sales offices and service centers all across Korea. Especially, our headquarters is located in Jukjeol, Yongin. And we have a solution center, digital plant, training center in HQ office to provide the most optimized and updated technology solution. So let me cover hydrogen. It's a very promising for us, but of course we also have to overcome challenges. For the opportunity, I think it can be a very good solution for us to deal with the climate change. According to the EIA Energy Outlook forecast, Asia Pacific's electricity consumption will be double the current levels by 2050. So, I believe we have to identify low or zero alternative energy future. But when it comes to current production method, we still have a high production cost and limited industry adoption at the moment. So it means that we need a lot of support from the government to reduce the original of the raw cost. So this commitment provides confidence to industry greater with investment that will bring costs down by making widespread adoption possible. Ensuring hydrogen delivers on the promise of a clean future. So I'm going to talk about the value chain in this slide. On your left side, you will see a lot of the different methods. I will skip this part for the sake of time, but rather I want to highlight how this illustration of the hydrogen value chain presents why H2 is such a viable and versatile zero carbon fuel source. So you can see there are many ways hydrogen can be produced, stored, transported, and used, but it can also integrate and coexist within existing energy networks and allow for smooth transition. That is why it is such a promising future level to decarbonize our existing energy demand. And this is very critical for us in Asia, since our region will double demand by, as mentioned earlier, but also because Asia was responsible for over half of the global carbon dioxide emissions in 2020, according to the BP Statistical Review of the World Energy 2021 report. In this diagram, you can see how hydrogen argument and support existing energy networks in both electrical grid and natural gas supply. Examples can be the production of the green hydrogen from solar and wind power electrolysis. This hydrogen can be stored and used to provide peak demand or stabilize supply when reinjected into the grid using fuel cell power plants. Of course, grid-scale battery storage is another alternative. But so it has a lot of the benefits, but for the benefit to realize all the benefits, we also have to overcome challenges in terms of scale and total life cycle cost. And there are many to plays regarding hydrogen, and there can be enablers and users. I think it's very difficult to meet the requirement from both sides. Let me cover the supply side first. The electrolysis technology and the OEMs, I think they are the most critical piece. So regarding that, Emerson want to make sure efficiency, scaling up, lean manufacturing, and optimize operation performance in terms of safety, reliability, and profitability. That's why we provide a customized, efficient consulting. Let me cover the customer side. It's, I think, all about smooth operation, moving into the smooth transition into the hydrogen. So it is simply a switch to cleaner hydrogen, and it goes with the financial stability, sustainability drivers too. To provide stable supply, we can think about many transport methods. But currently, I think the ideal way to go is the deployment of the electrolyzers where the hydrogen is intended to be used. So we can see that this instant many projects to supply industrial clusters, refueling stations, and even natural gas blending stations. In this regard, I think we need a stable and confident partners. Then, regardless of where you are in the value chain, whether you are in the technology, engineering side, or you are in the commercialization and integration part, waiting, who are sitting on the defense on the sidelines, or where you can be end users, we can make sure, regardless of your position in value chain, we will provide the best solution for you. We can optimize your work with the engineering solutions, regardless of what you need. We provide more than one solution to offer. We also have a lot of experience in complex integrated systems, so we can help with the fine tuning. Second, we are used to deal with the massive projects. Our organization is very flexible and have a support team all over the world. So we provide a product that is optimized in our factory, so we can provide it in no time. Also, this is our pride and joy is a digital ecosystem. Through this our digital ecosystem, we can help you operate in a safe, reliable, and profitable way. From 11 years ago, we have been working on accelerating the industry digital transformation and I believe that thanks to that, we have a very good advantage. Our target for engagement strategy is about partnering and making our customers successful in accelerating that hydrogen transition. Let me just briefly cover the emerging technologies stack in terms of the value chain. First, through the field instrument that is very accurate and reliable, we provide relevant data to you and that we can control. So by doing so, we can provide flexibility and the reduction of the cost in value chain. So all this smart data can be applied to automation process, digital twin, and simulation. Through this kind of data tools, we can provide accurate analysis and optimized solutions in no time to local or combined control systems. So based on the result, within the business field, we can enable you to make the best decisions for you through our applications. As I mentioned before, the key success driver is the end enablers and the end users. They have to create the value, so they need to establish the fast strategies without wasting any time. So by combining operation certainty, we can provide a service to our partners so they can make the business decision in the most efficient and quicker ways. Let me give you the one example from our production line. We have a lot of solutions under our belt. field instrument product line that is directly related to safety issue. This is about hydrogen leakage detection monitor. If you take a look at the left side, actually hydrogen doesn't have any smell, odor, and the explosion area can be quite wide, and it's very difficult to detect the leakage. That's a very tricky gas. But as you can see on the right side, depending on the types and the category of the hydrogen, we have a response to deal with it. So we have a gas detection group in general. So any type of the hydrogen coming from different position of the high value chain in hydrogen, we are ready to deal with it. This is Emerson Solution and Technology Portfolio, especially focused on digital transportation, digital management. This is called digital twin. Many industries are actually showing a lot of interest in this product. Eventually, smart plant and digital plant have been expanding. So in this like a digital twin, actually about the virtual plant that is identical to the physical plant. So they can actually simulate the operation conditions. Even they can try a different scenario that cannot be impossible to simulate in physical plant. So this is a very effective digital tool. Through the digital tool, we have a lot of benefits to gain. So mainly the benefit is the trials without damaging the process and the product. By doing so, we can increase the confidence in the operation, and we can also detect the any damages and at the earliest possible. So we can check all the tools before, and we can standardize the process for employees. At the same time, when it comes to plant relocation and expansion, from the design to the commissioning, we can reduce the construction time. So operation and maintenance time, we can also identify shutdown cases by providing optimized services. We also provide a continuous training for you to reduce any operation cost. Actually, at the first floor, we have a demonstration ready for you. So if you have any interest, please come to visit us. The next slide is about the remote control. Many industries are adopting remote automation, enabling technologies in an accelerating pace. So, within the plant, you can identify and remove any signs of the troubles, and you can, through this program and product, you can also produce very optimized product. All these are possible with a remote control and management. In relations to hydrogen industry, all across the country, we have a hydrogen-related refilling the charging stations, but everything can be managed in one center. The other example I want to provide is that solar and wind system can be also controlled automatically, and monitoring can be very easy. At this moment, Emerson Solution Technology make it possible to use the remote control in all our product lineup. So we will be the optimized partner for your business. Lastly, I want to talk about Emerson's leading effort to standardize the technology. As you can see in this slide, there are many research institutes and associations and academics we've been partnering with. So we have been contributing to the development of the hydrogen technology and standardization effort, so we can provide a sustainable technology as a best partner for your business. For the development of the hydrogen, I believe we are leading the world. I believe we will have many things to offer to you. Thank you very much for your attention. Thank you very much for the insightful presentation. I'd like to invite the third speaker, Jan Adowin, Director of the R&D H2WORLD. He will talk about advanced compression technology for clean hydrogen. Please welcome him with a big round of applause.
네, 시작해 주십시오. Good morning. I'm Jan Ardouin, R&D Director for reciprocating and diaphragm compressors at Howden. I'm very honored to have the chance to present to you today. And thank you for joining. This presentation is about advanced compression technology for clean hydrogen. So, after a short introduction about Howden, we'll see a reminder of the challenges related to compression of hydrogen, especially related to compression of hydrogen, especially in fueling stations, and then we'll go a bit in details about diaphragm and reciprocating compressors for hydrogen applications. I will finally present some recent developments in terms of remote performance analysis before concluding. So for those of you who may not be familiar with Howden, it was founded in 1854 by James Howden in Glasgow as a marine engineer firm, designing and building steam boilers and engines. Since then, it increased in international presence through acquisitions. Howden is a global leader in air and gas handling equipment such as fans, gas heaters, steam turbines, and various types of compressors. Our vision is sorry. Yeah. Sorry for this. Our vision is enabling our customers' vital processes which advance a more sustainable world. We have about 5,000 people in the world in more than 100 countries with 1.4 billion turnover. Howden has strengths in reliable product brands, among which you may recognize for compression Thomason, Burton Corblin, KK&K, Roots, and Peter Brotherhood. Howden is serving various segments such as renewable energies, of course, mining, power, chemicals, wastewater, and various industries. So, why is Howden talking about hydrogen compression? It's not new for us. Since the 50s, Howden has delivered more than 2,000 hydrogen compressors. So we think we know how to design, build, and maintain such compressors to the satisfaction of all our customers. Currently, for reciprocating and diaphragm compressors, we have a center of excellence in the Netherlands, a factory in Europe, factory in China, and packaging possibilities all over the world as close as possible to the end user, including a nice workshop, nice recent workshop in Korea. Brief reminder, if needed, of compression requirements in fueling stations that operate with gaseous hydrogen. There are multiple designs, of course, and the ones we most commonly see are shown here, whether production of hydrogen is on-site or remote. There usually is a compressor involved to store hydrogen at a medium pressure between 20 and 30 MPa, and then a compressor to feed the dispenser to fill for the vehicle fueling. There are some technical challenges in compressing hydrogen. First of them is safety, of course. It has been mentioned by in a presentation earlier today. Risk of leaks with hydrogen exist, and when it leaks, then the consequences can be critical. So safety for us, it means preventing hydrogen leaks as much as possible, controlling them when they can't be avoided to prevent any hazard for people first, and then for equipment and environment. Second challenge in hydrogen compression is about performance. The demands are changing today with the market as the infrastructure to produce, transport and distribute hydrogen evolves. There is a demand for higher capacities at higher pressures, and in some cases the expected performance are reaching or even pushing the limits of the current offers. Hydrogen is compressed mostly using volumetric compressors for efficiency reasons. Coping with requirement for viable capacity on large span is sometimes a challenge for such compressors. Reliability. Customer needs, of course, reliable compression system regardless how various or difficult are the operating conditions. Reducing unpredicted downtime is a topic that I think all compressor manufacturers are working on. One specificity with hydrogen is the difficulty to find suitable materials for high pressure and high temperatures to ensure reliability of the compressor all through the lifetime. Finally, a compression solution is always included in a complete system. So it has to be designed for easy integration in the process and plant. Flexibility needs to be offered by the compression system at the right OPEX, with the right footprint and the right interface for easy integration. Now, going a bit into the detail of the compressors, as I mentioned earlier, a short reminder on diaphragm compressor. Diaphragm compressors are a type of reciprocating compressor where compression stage is statically sealed and layers of metallic diaphragm are ensuring the gas remains free of all contamination. They usually can achieve higher pressure ratio than other type of compressor, with capacities that do not go as high as the ones of piston compressors. There is a history of using such compressors on high pressure application with references, for Howden at least, up to 200 megapascal. Achieving long diaphragm lifetime with frequent start and stops is one of the limitations we manufacturers are working to overcome in order to provide the flexibility in operating condition that is expected by the market. I mentioned earlier a challenge on material compatibility. Metallic materials can be subject to two types of issues in presence of hydrogen: high temperature hydrogen attack and hydrogen embrittlement that leads to material premature failure, which means safety hazards and plant downtime. Risk of hydrogen embrittlement depends on hydrogen pressure and temperature as well as on material condition, and it's not really possible to predict. Pressure containing part in compressors, especially where the compression happens, are in addition subject to varying mechanical stresses caused by compression cycles that happen several times per second. So far, there isn't really international standard or guidelines related to the design of compressor for these specific demanding conditions at high pressure. Some literature mentioned here and technical reports can be found, but they unfortunately do not contain simple or definitive answers regarding the choice of materials. That's why we, as OEM, are relying on our experience records, and we are continuing our researches and tests. Customers often specify stainless steel for hydrogen compression. There are indeed stainless steel materials such as H2WORLD that are known for good compatibility with hydrogen, but have low mechanical property. Some other materials with better mechanical properties, such as AISI 630 or 17.4 pH, are highly subject to hydrogen embrittlement, which seems to be sometimes ignored. Mentioned already, hydrogen is difficult to seal due to the small size of the molecule and the low viscosity. Diaphragm compressors are statically sealed, and the correct design of a sealing system meeting requirements of high pressure, rapid decompression, and pressure cycles is complex. We have analyzed that when compressing at high pressure, regardless of the choice of material for the gas and oil plates in the diaphragm compressor, the impact of deformation of these plates on the sealing capacity is far from being negligible. As shown on the right side of the slide, the plates, even the very thick ones, can deform during the compression cycle up to a value that causes a radial movement at the contact area between the plates and the seals. And this radial movement, due to the deformation of the metallic materials, is impacting the sealing performance. Of course, finite element analysis is a precious tool for studying at high pressure the design of this equipment. The control of the clamping force between these two flanges is critical to ensure the compression stage integrity. It is better done by measurement of the elongation of the bolts rather than by only the measurement of the applied torque, which has proven on site to be not a reliable method to control the clamping force. We have tested and we continue to test several types of seals to find the optimized solution for high pressure. We have tested simple metal O-rings, and we've tested various types of spring-energized metallic rings. We are investigating the possibilities of using non-metallic seals with our own research and testing program. So we're doing tests with various types of gas, including tests with hydrogen at 1000 bar. Now, a few words about reciprocating compressors for hydrogen compression. What you can see on this slide is a compact skid for a 6-stage oil-free compressor that raises pressure from atmospheric pressure up to 20 megapascal. Some of the compression stages include free-floating piston technology to reduce the ring wear. The compressor is driven by a VFD to offer capacity, flexibility with minimizing power consumption. This is a modular solution. The base case included these 6 compression stages, but solution with 3, 4, or 5 stages using some of the same modules are also available. Modularity is what is helping us with standardization of parts and components, which is what the market needs to lower the cost and ensure deliveries can scale up with the demand. These compressors are equipped with an online performance analysis system. So Howden has developed a platform named Howden Uptime that is available for all the types of equipment of Howden, fans, turbines, compressors, via a web portal. The format, screens, and data available, of course, depend on the customer needs and on the machine that is analyzed. These are examples of data that are available on this portal for diaphragm and for reciprocating compressors. Some of you may recognize here PV diagrams, pressure measurements, or vibration measurements. Both of these solutions use physics-based digital twins to analyze the actual performance using the theoretical performance calculation models that are fed by data coming from the customer sites. The portal offers quick and easy access to compressor health check, which can be partly automatized. We have the possibilities to always customize the solution for an easy integration in the customer system, including integration in the control systems where we can work with partners. I know digital twin was mentioned by Emerson before. There are obviously synergies here. Now we'll take a bit of deep dive on detail of this online performance diagnosis system and why it can help to reduce downtime and why it's not just a monitoring system. So looking at a specific example for diaphragm compressors. When zooming on one of the graphs that is accessible on the main page, we can see the green curve here, the light green curve, is the actual oil pressure in the compression stage measured over one cycle. So all these measurements is less than 1 second. So we are using high frequency pressure transmitters to understand what's happening inside the compression head. The blue curve is what represents the digital twin, how the compressor was supposed to operate exactly in these same conditions. So the tool is enable us to add a signal on the same graph where needed, so provided, of course, the sensors exist. And here we have added signal from accelerometers that are installed on the compression stage. On this view, so you can see that the accelerations correspond to the first acceleration shown here correspond to the beginning of the suction phase, so it corresponds to the opening of the suction valve. The acceleration in the middle, sorry, I was looking for this middle of the graph, is the bottom dead center of the stroke. And the third acceleration is the opening of the discharge valve. With all these signals, our experts can easily understand if the compressor is operating under normal operating conditions or if something is wrong, either in the phasing or in the expansion cycle, in the suction phase, in the discharge phase. How does this enable uptime for the compressor? Now we'll see that a bit later. Sorry. Zooming on another graph, we see these typical pressure volume diagrams, so they are typical of compression cycle. And again, we are superposing the actual site values and the digital twin. This is what our experts use for diagnosis on power consumption, for example. This pressure volume diagram can also be used to detect anomalies such as valve malfunction. For example, a delay in closing or opening a valve or a leakage of a valve would be visible on such a graph. Mentioned earlier how these tools can be used to minimize downtime. This is an example. At the moment these data were measured, no anomaly could have been visible at site by only looking at the compressor output or the compressor performance, as the gas pressure was still delivered normally. However, when we look at what is happening inside the compressor, we compare it to the theory, we see that the shape of the actual oil pressure cycle is different from the digital twin. You can see here the digital twin says there should be a pressure increase, and in reality we did not have this pressure increase. There is an unusual pressure dip at the end of the suction phase in the compressor, right in the middle, and it corresponds to the bottom dead center of the stroke. This means to us that there is a lack of oil in the compression stage during the cycle, lack of oil on the oil part. The analysis of the trend on this pressure dip and oil peak would give an insight on the root cause, because the root cause would be different whether this anomaly came suddenly or appear progressively. Insight on the root cause of the issue obtained remotely contribute to reduce downtime, for example, by enabling us to tell the customer to stop the compressor for inspection before critical failure occurs, or simply enabling us to fix the issue quicker, because we don't need to do the diagnosis on site. The diagnosis is done remotely. The first time a field service engineer goes to the site, he has the right tools, the right diagnosis to fix the issue quickly. Finally, we have seen that the requirements of high-pressure hydrogen applications are not yet fully addressed by existing solutions and are evolving with the market. These are exciting challenges for compressor manufacturers and for integrators. Two types of challenges. One is expanding the limit of the existing technologies, looking at higher pressure for non-lubricated reciprocating compressors, investigating possibilities of larger volumes and extended mean time between maintenance for diaphragm compressors, and lowering the levelized cost of compressed hydrogen, talking both CapEx, OpEx. Another type of challenge is combining new and alternative technologies with the existing know-how and hydrogen application expertise. And I mentioned new and alternative technology. I'm thinking about the digital ecosystems and tools to improve the services to customers, alternative compression and storage technologies such as electrochemical compression and metal hydrates, and the use maybe of liquid hydrogen where compressors can also be involved. That's all. Thank you very much for listening this morning.
Thank you for nice presentation. Thank you. 자, 다음.
Next, I'd like to invite Kim Kyung-hee, President from H2 Please welcome the speaker with a big round of applause. She will talk about carbon-free 2030 challenges of Korea. Hello, ladies and gentlemen. I'm Kim Kyung-hee from the H2 Today I'm going to talk about, as you can see in the slide, hydrogen happy town. I understand this is organized by the Hydrogen Energy Association. I understand this is not perfect yet, but we are still making big progress. Please listen carefully. So our focus on hydrogen happy town, focusing on carbon-free 2030 challenges of Korea. First, I'm gonna talk about the features of the hydrogen energy, and then I will move on to the hydrogen happy town project. First, what is the unique about hydrogen? It is clean and safe energy. At the same time, it will never be running out of it, so it can be recycled. On the other hand, fossil fuel has a lot of the issues, as you know, for power generation and transport. And that has a lead to climate change, unfortunately. So we are moving into the renewable energy area, and eventually we have to go for hydrogen era. Especially hydrogen can be very good. It can be applied in many different areas, from heating to transport to power generation. And by utilizing the nuclear power plant, we can also create the hydrogen and we can replace many other energy sources. Second special features of hydrogen is that energy storage and the large scale of the transport. It can also serve as energy storage. We've been covering a lot of the production by other speakers, but let me briefly talk about green hydrogen and blue hydrogen. The cheapest one is the blue hydrogen, and that is the main types of the hydrogen produced in Korea. And according to the Korean institutes, LNG can be also turned into hydrogen through the reformers. At the same time, hydrogen, this energy storage and then large scale transport, we have to deal with a few challenges because we have to change the types of the hydrogen. We have ammonia style storage and many different types of storage. And we have a tank or pipeline to deliver hydrogen. I think that is what the Ulsan is using. The Dutch is also using the LNG existing pipeline for delivering hydrogen. This is the blueprint for hydrogen city. By using hydrogen, we can supply the energy to vehicle mobility. Also, it can be used for the tourism too. Now, what is exactly hydrogen city? In line with the association, H2WORLD has been developed. This hydrogen happy town is about utilizing hydrogen to establish a new type of the city, and then we promote this idea and we want to export this expertise to other countries. The core part of the hydrogen city is the eco-friendly circulation of the energy. The food waste, combustible, the waste can be turned into the biogas, and then it can be used to create the hydrogen. And then we want to deal with it, treat them in a safe way. So it can be seen as a one cycle of the energy resources. So by definition, this is about establishment of the ecosystem of the hydrogen, involving many citizens to create a clean city. I will go back to it later. If we take a look at the overseas examples, there are many focusing on about transport and energy utilization. So mainly they are focusing on hydrogen vehicles and hydrogen station. But on the other hand, our system, our hydrogen ecosystem is about utilizing it in many different fields, even by adopting IoT and big data. First of all, so by combining existing energy and combining supply and supplier and the demander together, we can create the database city, and also we establish the carbon-free model, so we can realize the citizen-friendly cities without any pollution or high carbon emissions. So the city can provide the energy self-efficiently. And also, when it comes to utilization of the energy with the hydrogen, there will be mainly focusing on the residence and transport. So we can use these also based on the residence and transport utilization. We can also have the integrated operation system, and then we can also have a connection with other industries too. So by utilizing renewable energies, we want to create the green hydrogen. Biogas can be used to create the hydrogen for future, and also based on the localized technology, we want to producible reforming technology. And also, by utilizing the combustible waste resources, with that current technology, we can create the 8 tons of the hydrogen. One vehicle can be charged to cover a 5-kilometer driving distance. I think that's enough for now. Let me move on to the hydrogen happy town. These are the countries we've been benchmarking for getting the idea. This is a Denmark case study. So they conducted the demonstration business by the 1980s. They are actually almost like wasted land. However, they create the wind renewable energy complex zone, and they revitalized, and they created 60,000 megawatt for electricity production with a 72 wind facility, and they even export their electricity to other areas. Even though they have only 100 households, they are reborn as a mecca for hydrogen village. And by 2020, they connected 35 households with hydrogen, and then each household has a fuel cells for installment. And also they aim to create the artificial energy island for the first time in the world. So they can create electricity cover the 1,000 households, and they can be used for heating and things like that, so they can be energy self-efficient in their village. I want to introduce another example from UK. They have a lot of interest in hydrogen, and they have conducted many different pilot projects. For the first time, Leeds from United Kingdom aim to create the hydrogen city for the first time in the world. By 2030, they are conducting ongoing H2WORLD Leeds City Gate project, and they also declare that they will reduce to zero emission of the carbon dioxide by 2050. And also they want to create the more utilization of the hydrogen by adopting the pipeline from the LPG. So they believe that they can go ahead with 100% for hydrogen utilization. And also they are using the salt cave. They use that for storage of the hydrogen. So they can reborn as a city that is very environmentally friendly to all the residents. So it can be economically viable and efficient to heat up the village. Next, I'd like to talk about the Dutch cases. They are showing a very good example too. In northern part of the Netherlands, they also create the green hydrogen city for the first time in the EU by utilizing 1 megawatt solar panel they established a facility to create the 270,000 tons for electricity, especially with the electrolysis. So eventually they want to create a 10 gigawatt for energy production by 2040. And they are actually also have an ongoing project called Poseidon in Northern Sea. So they are by using the electrolysis technology with the seawater, they want to turn to electricity 100%. So every year they can reduce emission by 16.5 KT. Actually, they already have a natural gas pipeline. They want to convert this natural gas pipeline into the hydrogen pipeline, so they can be used for industry and also residence heating system. This is a mock-up visual for the local hydrogen city. So they want to provide energy with a hydrogen production, and this city includes the hydrogen, not only the hydrogen production facility, but also hydrogen combined station to school and everything. This is our basic concept for hydrogen city in Korea. And the next slide shows how we can supply energy with the hydrogen. As you can see, there's a residence, office, and also leased apartment and hotels. All different types of the housings can use the pipeline for hydrogen. So the electricity and heating can be provided. And when it comes to transport, one area can cover the providing the electricity, and the other area have a charging station to support the supply of the electricity in a stable way. As you can see, when it comes to supply, underground, they have a facility to make sure there's a smooth transition of the mobility, so they can provide the energy in a smooth way. This is our concept. And then this is our main part regarding the transport. We want to create the ecosystem that involves the transport and hydrogen all together. We don't want to miss out the convenient places. We can even adopt the drone, tram, bus, and heavy-duty trucks with the hydrogen technology to create cleaner city. Next, let me talk about the residential issues. Still, many houses are already using the solar energy, but they have the storage limit. So eventually we have to go for hydrogen. So now even the independent household can install the equipment to provide electricity, and the large complex of the residence can also have a bigger electricity power. And commercial building is the same. Hotel, office, they also have their independent individual electricity supply. I think the public area will be the same. They will have no problem to get the supply of the electricity with this hydrogen technology. Next, this is about example. We want to utilize hydrogen energy. So even in the park, we can be energy zero park. Even in the housing, residential housing, we can also use hydrogen to get the energy and the heating. We can have hydrogen staging stations. We can use the hydrogen vehicles. We can use the LED light for highways. All these efforts can lead to a reduction of the energy consumption. So all these are possible thanks to the platform establishment. This is our plant. At the same time, smart farm is also very popular within the city. As you can see, hydro is no exception. By using hydrogen, we can even create the smart farms. We can produce produces, and some can be even used for medical purpose. There are many applications possible. The next one shows that this is Ulsan city. This is a research we've been focusing. Ulsan is trying out the demonstration business. Ulsan can be one test bed for the technology. One of the benefits is that Ulsan create the many byproduct hydrogens. This is a benefit we can try out the technology in Ulsan. And through many housings, we can also provide this technology to the nursing homes and the public areas and many different types of the areas. As you can see, we are in the plan to establish the hydrogen city. So all depends on how we can create this ideal city, hydrogen city. The study is still ongoing to support that concept. Well, then what about the pipeline? This is one example of the layout of the pipeline. This is our vision. I believe that the hydrogen city will be created within Ulsan. Thank you very much for your attention.
네, 좋은 발표 감사드리고요. 네.
Thank you very much. Now we finished the whole presentation. I would like to invite the two more presentations. Then we will have a short break before the panel discussion. And then we are moving ahead with the next speaker. We are inviting.
We'll have a Ji-Hoon-jo from Korea Intellectual Property Organization. He's going to talk about Korea's hydrogen industry's competitiveness analysis from patent point of view and R&D strategies. Good morning. My name is Jo Ji-Hoon. I'm from Kipo. And the hydrogen economy became a buzzword in Korea. And it is honor and pleasure to have you make a presentation in front of you. So today, this topic is our R&D strategies as well as a hydrogen industry's competitiveness from patent perspective. So you've seen many reports on the competitiveness of hydrogen. So from patent perspective, you can see out of this session that we can actually analyze this from hydrogen or patent perspective as well. So as you may know well, so actually the transport storage is really important. So to emphasize this point, so let me briefly explain our hydrogen ecosystem. So because of global warming, so carbon neutrality is a must. So especially in the US and Europe, they're introducing carbon border tax. So it poses a realistic threat to Korea. So it is really urgent to switch to low carbon industrial structure. And hydrogen is a key energy in making this transition because solar wind powers, renewable energies actually hydrogen is the realistic solution that can minimize carbon footprint. So the demand, hydrogen demand is expected to increase globally. So establishing infrastructure and also delivery system is really important. So how to secure hydrogen is really important. So let me briefly explain the global status. In a previous slide, I talked about hydrogen supply issue. So global, in order to establish a supply chain, so there is a diverse cooperation going on between many countries with technologies. And as you listen to the previous presentations, and Japan has a brown core from Australia. Also, Brunei has a reforming hydrogen, and Saudi Arabia has also hydrogens. So the economy is actually working hard to establish supply chain for hydrogen. So because of some differences, natural differences, so it is necessary to establish a global supply chain. So the competitive production and storage, I believe there is opportunities in these areas. Let me explain pattern trend. So in the past 20 years, you can see the trend of pattern application across the world. In 2003, President Bush introduced a hydrogen initiative, and they ardently started investing in infrastructure for hydrogen. So you can see the number of patents in hydrogen increased dramatically, and also as fuel cell patents led this trend, and not just the hydrogen car, but also drone and hydrogen shipping, hydrogen train, and hydrogen train. So as we see more applications, so hydrogen transport and storage are actually leading the number of patents. So let's take a look at the status of at technology level, hydrogen technology by country. It looks a little bit complicated, but we can analyze a lot of data based on patents. But this is a simple analysis on statistics. So you can see a patent intensity means the number of patent applications. So if the patent application, if there are a lot of patent applications, there is a lot of R&D. So you can see hydrogen production, fuel cell area, you can see a lot of patent applications, meaning that there is a lot of R&D activities going on in this area. And if you look at the y-axis, you can see the patent influence. It refers to the technical level of each country. So how this is calculated? So when the patent is applied or filed, so we are supposed to measure based on existing technologies. So meaning that it is very valuable technology. So if you look at patents, so we count on these technologies to make this graph. So if you look at the United States, across all hydrogen areas, they are blue. Actually, America is blue. So they have a high technology level, and below that you can see Japan, Germany, Korea, and China. So right-hand side, you can see a more simplified version. And if you look at this diagram on the right side, gray is the U.S. So in production and fuel cell area, the U.S. has advanced technologies, and if you look at other countries, they are somewhat clustered. So what we can tell from this graph is, so when it comes to production and also development, it will be very difficult to overcome the obstacles raised by the U.S. And also in infrastructure areas, still there's not much activities going on for technology development. So if we focus on these infrastructure areas, then we'll be able to achieve some tangible results. So this is how we see this graph, interpret this graph. And in the previous diagram, so I mentioned the promising areas, which are transportation and storage areas. So let me give you more details. There are 4 areas One, A is a plant, B is delivery, C is a transportation mode, and D is equipment. So it's not that much different from the previous status, but when it comes to LNG carrier and pipelines, Korea has a lot of experience in this area. So as you can, it doesn't show, but when it comes to transportation, Korea has a lot of competitiveness. Let's take a look at the core technology trend for transportation and storage. You are the expert here, but let me briefly touch upon the trend. First, liquefaction hydrogen. So three major companies, Air Product, Linde, and Air Liquide are dominating this market. So they are designated as a business secret, and they are regulated items. So that technology is banned from sharing, and also with Linde and Hyosung, there is a joint venture between Linde and Hyosung recently, and also SK actually acquired a shares from Plug Power in the U.S. And the last one is a national trend. KOCAS has a LNG, a cold energy national project is going on. So there are three ways to secure core technologies in an liquefaction hydrogen. And if you look at the trend of patent applications, in the past it was focused on storage containers, and recently it is shifting to hydrogen liquefaction. For example, cold LNG, cold energy, hydrogen liquefaction, and also and charging system and liquefaction hydrogen carrier. So this is being developed to use a limited space, and also Korea and Japan are leading these areas, and Japan is slightly ahead of us. So Japan is actually reached the demonstration stage for LOHC carrier. And Japan's Kawasaki heavy industry is also ahead of Korea's Samsung heavy industry in terms of the number of applications. And GTT is also has a potential to expand their businesses into these areas as well. And next is the trend for transportation and storage. And in this graph, you can see, so the carrier, there are actually the number of patents, about half of the patents submitted are happening in carrier. So this is divided by specific technology, and red graph shows increase, recent increase. So plant and anhydrate, and also pipeline, turbo expander, and ultra low temperature. And you can see the intensity. So intensity means that in specific technology area, a single company is dominating the market. It can so this is for your reference. So let's take a look at the number of applications, storage and extraction plant, and delivery carrier. So existing companies are actually expanding. Energy companies are expanding to these areas. And also when it comes to a transportation, actually Kawasaki heavy industry is in dominant position. And also you can see more and more companies moving to these areas as well. Then based on this data, let me explain how we can set up or develop strategies. So when it comes to hydrogen production, there are many diverse technologies, and to analyze these technologies, I selected a few patent indices. And so actually, when it comes to reforming, we have a high number of patents. So we can say that Korea has active activities in reforming areas, and also there is other increases. So based on this pattern data, what we can learn from this analysis is that in a short term, we can advance natural gas reforming technologies so that we can secure volume hydrogens, and midterm we can focus on green hydrogen, and so we can draw these lessons from this analysis. And also next is a fuel cell. And down below, you can see 4 major countries have diverse fuel cells. So we actually quantify their pattern influence. Thicker the color means that the higher the technology level is. So Korea. So when Korea develop fuel cells, Korea will face many technology obstacles or walls, or dependent on the United States in developing technologies in fuel cell area. And this is the last slide. So let me summarize the implications from this pattern analysis. First, so we need to focus on research and development for core hydrogen transportation storage technologies. So we are importing technologies, but it's not actually easy to get the technologies from other countries. Otherwise, we'll be dependent on other countries. And also, a liquefaction and metal hydrogen compounds will dominate. Actually, the technology in this sector will dominate, will determine the market also. And hydrogen carrier technology is key to green hydrogen distribution of the world. And also, Korea is a latecomer in this area, so we need to secure core technologies so that we can pursue partnership and collaboration with other countries. And lastly, and I'd like to emphasize this, Korean industry is in its infancy, I believe. The hydrogen industry is in its infancy, I mean. So since we are in the beginning stage, we need to file for many patents so that we can invigorate this sector. So source patent or a influential patents need to be pursued at this stage. So even if your patent is rejected, try to take a wide approach or broad approach. So try to make a ambitious and bold application. And this is the last slide of the presentation, and you can see technology trend for, I believe that this we need to pursue these directions for each sector. Thank you for listening.
네, 좋은 발표 감사합니다.
Thank you very much. Next, I'd like to invite the next speaker from Siemens, Kim Young-tak, Director from Siemens Technology, Siemens Energy. He's going to talk about Siemens Energy's green hydrogen production and P2G solutions. Please give him a big round of applause. Hello, ladies and gentlemen. I'm Kim Young-tak from Siemens. I'm in charge of the business development regarding the hydrogen. First, let me brief. I'm very happy to be here to present the Siemens energy strategy, and I want to focus on the solutions in terms of the hydrogen value chain. I'd like to also share the ongoing projects in Siemens. So let me briefly introduce our company. About 2 years ago, it was a part of the Siemens group, but we actually became the separate company, subsidiary focusing on Siemens Energy. As you can see in the slide, we've been conducting business based on the conventional energy sources such as oil and gas convention, transmission. These are our main business regarding the conventional power. But recently, we are going for eco-friendly trend. So the technology focusing on the power generation from the fossil fuel, now we are converting that technology into the hydrogen based. So let me cover the current technology. We are focusing on 500 megawatt H plus technology. I think we can combine 50% of hydrogen, and we have also smaller scale, 50 gigawatt gas turbine, and we also have a 75% hydrogen in that system. In 2030, we aim for 100% use of the hydrogen. And also by 2030, we want to create the hydrogen turbine. For transmission, it can be connected to the renewable energy sources. So at this moment, turning into the hydrogen economy, we recognize the importance of the hydrogen. And then we established a new energy division. They are in charge of the covering the hydrogen part in the value chain. And we have also another subsidiary that is only focusing on the wind energy. So let me cover the new energy business. You can see we have under new energy business, we have 3 pillars: hydrogen systems, power to X solutions, and energy consulting and digital services. Today I'm going to focus on mainly our facilities and solutions in the new energy business. First of all, why we want to pay our special attention to hydrogen, even by creating the new energy business division. In Europe, hydrogen has been ready from the early stage. They are before Korea to start the hydrogen business. This is all about our concern to reduce the carbon hydrate. So this slide shows that where the most CO2 is emitted, power is coming from 42% is coming from power, and transport covers 25% of the emissions. Actually, when it comes to power, it's easier to reduce the CO2 because there has been many technology and many business developed in this field. So I believe that many parts will be turning into the renewable part. I think it's about 27%. And given that we have more and more renewable energies, we have issues regarding renewable energies because they are lacking in sustainability about the stable supply of electricity. So we have to think about how we can resolve this issue. And then there is a wasted electricity, and we have to capture the byproduct, the wasted energy of electricity. So the bottom line is how we can utilize the wasted energy. That's why hydrogen comes as a solution to that issue. They can be even applied into different fields with a sector coupling concept. So that's why we've been focusing on hydrogen. So we started with the electrolysis. Through that process, we secured the technology of hydrogen with alkaline and the PEM methodology, SOEC, high temperature electrolysis. We believe that PEM is the most competitive technology at this moment because they can cover the unstable supply of the electricity with the renewable energies. The best part about PEM is it's very easy to turn it on and off. And regarding the environmentally friendly materials, I think we can provide cleaner energies. Also, regarding the price, I understand that many people are concerned about the cost, but with the PEM, we are using the expensive platinum. I understand this is a part we have to work on. But at the same time, when it comes to operation, regarding the operation cost, I think there will be no additional burden. So this is a benefit by adopting PEM. So in 2011, we started the left scale project was started. In our roadmap, every 4 to 5 years, we've been increasing our size capacity by 10 times. So based on this roadmap, currently we are covering 10 to 20 megawatt, but by 2023, we are aiming to create a 100 megawatt. And by 2028, we want to have an ambition to create 1,000 megawatt. So this is our biggest capacity product called Sylvia 300. We upgrade this product from the last model, and efficiency level reaches 75%. As you can see in the slide, you can see this module. It looks like an Apple box. It has 24 modules. It's called full array, and it covers 17.5 megawatt of plant power demand, and it has more than 75% plant efficiency. As I mentioned before, for the production of the green hydrogen, the cost and production cost is about the electricity price from the renewable energy or capex. So we already recognize issues. But because we are using platinum as a catalyst, when we go for scale up for production, we can even realize that the economies of scalability to bring down the cost. We haven't officially announced yet, but we plan to expand our facility to gigawatt capacity. And then we also have a pre-engineered products, so we can standardize product to provide it to market. All these efforts will lead to reduction of the cost. As you can see on the left side, this is our process. We are in the process of going for the standardized product. And at the field, to bring down the cost, we want to go for the prefabricated method. On your right side, you can see the picture of the factory. We also have automation to bring the best advantages. So from the 2015, based on the mainly based on the European nations, we have a lot of the demonstration business regarding the hydrogen electrolyzer technology. You can see them in many different fields such as mobility and energy and industry. 6 megawatt in Australia is the biggest size currently. In Europe, there are more projects planned. There are many about more than 3 megawatt size in France. Even they are aiming for 200 megawatt and above. So let me briefly introduce H2 Future program. In Austria, there's one famous steel company. One of the biggest supplier of the CO2 is actually steel making. That's why these makers are very much making effort to reduce the emission. H2 Future is a project funded by the European nations. In this project, they are using our product called Silza 300. The scope is connected to the wind energy to produce the hydrogen, and that energy can be also used for heating in steel making facility. Some part has been used for research in collaboration with other institutes. And these are the basic information description of H2 Future. And then I want to introduce one more project called Haru Uni Pilot Project, which just started this year. And this is partially funded by the German government, and also it is also funded by Siemens too. The project is ongoing in Chile. Eventually, we will involve many stakeholders. I will go back to it later. As you may know, Chile has a very good wind quality. It means that we can reduce the renewable energy price. So we can create the electrolysis with a better price competitiveness, and we adopt a direct capture methodology. We capture CO2 in the air and store them, and then the nearby industry areas can also capture them, and they can use it to create the methane. That's the one way to create hydrogen first, and then it can be used for in German cases for demonstration business. And that can also turn into gasoline too. After that, e-fuel can also use the IND for sure. They want to use it for develop the engines in Porsche also participated as a player in this project. So they can apply this case to vehicle business. So this you can see the layout of the site. You can see each facility in this picture. So this is they have a storage and they have a MTG process, turning them into gasoline, and this gasoline is used for Porsche for mobility. So there are many partners involved in each different step, and there is ongoing project called Haru Oni pilot project in Chile. Besides that, we have making many efforts to go for zero waste. And we've been going overseas with more than 90 countries. So by utilizing our tight-knit network of the countries, we have accumulated many experiences. So in Europe and in the US, we also have the combined energy facilities. As you can see, we have a Braskem, Brazil's chemical plant. We have a small turbine to use 60% hydrogen energy this year. This year, we commissioned this project. So all around the world, to have a carbon-free society, we have promoted many projects. So I understand that this hydrogen technology is still early. So our current focus is that we want to accumulate many experiences. So we want to create many reference applications, and then we target to enhance partner network. Not one country can make it happen. Without partners, it's a too daunting task to catch up the technology. So we are under review to have more partners, and internally we also focus on automation of fabrication supply chain to reduce the cost and then also reduce the capex operational expenses. And lastly, we will spare no effort to have a technological improvements given that we are technology-based company. So we are currently supplying the product related to electrolysis, but we are conducting RA related to other technology too. So high efficiency Power X solution will be our next focus. Lastly, if we have one more opportunity next year, I want to introduce Korean cases next year. Thank you very much for your attention. It's great. Every speaker has been very punctual. So I hope we can have a lunch earlier than expected. So I'd like to invite the next speaker. Mr. James Taylor from the Mott McDonald. He'd like to talk about the hydrogen value chain. Please welcome me with a big round of applause.
Okay, good morning everyone. My name is James Taylor from Mott McDonald. So I'm not a technical expert specifically in hydrogen. So I'm looking at the situation from a holistic value chain perspective and looking at how the pieces fit together. So any numbers quoted should be treated with a healthy disdain, and they are only to represent an order of magnitude. I think this is normally where I'm supposed to give the marketing material all about Mott MacDonald, but I'll try and keep this to a minimum. So for those of you who are not familiar with Mott MacDonald, we're a global multi-sector engineering management and development consultancy. We're working in around 150 different countries, and we have around 17,000 staff. In Korea, our office is based in Seoul, and I would be happy to welcome any of you at our office anytime. So, there are three main production pathways for hydrogen, determined by the level of carbon emissions attributed to the produced hydrogen. These are commonly referred to as green, blue, and grey. Currently, green hydrogen makes up around 1% of the global hydrogen production. Production and supply costs are not yet competitive for green hydrogen to be adopted in the majority of potential end-use sectors, and the supply chain is still in its infancy, and large-scale electrolysis technology is still being developed to enable the mass production of hydrogen on an industrial scale. So today I'm going to touch on some of the following topics related to hydrogen value chain, so looking at production, transport, storage, end use, and where are we in this journey. So, as the world is increasingly looking towards cleaner energy systems in an attempt to tackle climate change, hydrogen is expected to be part of the solution that could help make many countries arrive at a net zero carbon emissions environment by 2050. At Mott MacDonald, we are seeing growing client demand for sustainable hydrogen and are increasingly involved in related work. Our hydrogen team is involved in many of the first-to-market hydrogen projects, such as the Nord H2 project, Europe's largest green hydrogen project, the UK's first multimodal hydrogen transport hub in Teesside, and the first hydrogen train in San Bernardino, California. Our team can provide technical advisory and economical advisory services, owner's engineering, design, program and project management, as well as various other services. So hydrogen is an energy transfer medium, an energy vector. There are various pathways by which hydrogen can be produced and its possible end uses. This applies to the number of sectors or end users as shown here, such as power and transport. The production route determines the decarbonization credentials of the hydrogen, whether CO2 is emitted in its production. So here we'll look at some of the hydrogen production technologies. So alkaline electrolysis is characterized by relatively low capital costs compared to PEM electrolyzers due to the avoidance of precious metals. However, PEM electrolyzers are more compact and offer more flexible operation. So many current projects are looking to make use of the alkaline electrolysis systems, and the PEM is in a much earlier stage of deployment, with 10 to 20 megawatt systems now being planned. Electrolyzer costs are relatively well known, but have a wide range, depending on project-specific requirements. Future costs are uncertain, mainly reflecting the market uncertainty and the supply chain immaturity. However, there is an expectation of substantial fall of OEM manufacturing capacity builds up and automates, so prices are widely tipped to halve by 2030. Renewable electrolysis is expected to generally become competitive with blue hydrogen during the 2030s. So steam methane reforming is still the primary method of which hydrogen is produced today for industry. The reforming reaction between natural gas or a biogas and steam under pressure in the presence of a catalyst produces H2CO and a small amount of CO2. Steam reforming can also be used to produce H2 from other fuels, including ethanol, propane, and gasoline. So gasification is also one of the methods, using a controlled amount of heat, steam, oxygen to produce H2, CO, and CO2 from coal or even biomass. Gasification is carried out at high temperatures, over 700 degrees C, without combustion. Pyrolysis is carried out in the absence of the oxygen and can be used as a prior step to biomass gasification to produce charcoal and tar for gasification. The net carbon emissions can potentially be low by growing biomass that removes CO2 from the atmosphere or using carbon capture and storage. So transport options for hydrogen, those include pipeline, blending into existing natural gas networks, or 100% hydrogen in repurposed or new pipelines, truck or trailer transportation of compressed or liquid hydrogen by road or rail, or shipping as liquid hydrogen, or conversion to ammonia or liquid organic hydrogen carriers. Due to its low volumetric energy density compared to traditional fuels, this makes transportation and distribution a challenge. Transport and storage costs of hydrogen will have an impact on its overall cost and competitiveness against other fuels. This will become increasingly important as the cost of production declines. The most advantageous transport option for hydrogen will depend on situation-specific factors such as location, distance, and volume to be transported, and the required end-use parameters. Today, distribution typically involves trucking of compressed or liquid hydrogen, with hydrogen pipelines in use for some industrial settings to transport feedstock. For future export to enable a global hydrogen market, hydrogen shipping will need to be developed further. So hydrogen can be stored, as we know, as a gas or a liquid, with the gas storage requiring high pressure and large spaces, and storage as a liquid requires cryogenic temperatures. So at the moment, currently the most commonly used method is using the steel tanks. But geological storage is also an option, with salt caverns being touted as the most cost-effective, which is attractive for industrial and power applications. So here is an overview of just 7 of the sectors where green hydrogen has good potential to be used. And I think over the last few days we've heard about many different applications and sectors that hydrogen can be used. And as the hydrogen technology and hydrogen economy evolves, I'm sure there will be potentially many other new and existing sectors where green hydrogen can play a role in moving towards decarbonization. So here in Korea, what is going to drive the growth of hydrogen? Key legislation and things such as the Hydrogen Economy Roadmap, the Green New Deal, and the Hydrogen Law are all setting the framework for hydrogen in Korea. Korea is looking to decarbonize to meet its carbon neutral 2050 pledge. There is a push for reduction in air pollution and ultrafine dust emissions. There is a move to increase energy independence and reduce reliance on fossil fuels for power generation. And this is all where hydrogen can play a part. Korea is looking to become one of the world's leading hydrogen economies, creating new industries from transportation to energy, stimulating increased investment and job creation through expansion of downstream industries. So as mentioned earlier, hydrogen production is around 70 million tons, from which the vast majority has been through SMR of natural gas, with the majority of the end use being ammonia and then fertilizer, and in the use of hydrocarbon cracking and synfuel production. The scale of the challenge is large. Green hydrogen is still only around 1% of global H2 production. So while Asia cannot be thought of as a single entity, there are very similar drivers and issues, and there are a few overarching themes that arise in the densely populated developing countries and regions in the Asia Pacific. Energy security, population growth, energy consumption increases. Hydrogen can provide a readily available and flexible energy source with a low environmental impact. So there are still several key barriers and constraints that need to be overcome. Electrolysis manufacturing constraints. Global manufacturing capacity is expected to rise to 3.1 gigawatts per year by the end of 2021. A total installed electrolyzer capacity of 5 terawatts by 2050 will be required, up to 50 times the expected manufacturing capacity of 2021. Competitiveness of green hydrogen. Due to the current cost of renewable energy and the electrolysis constraints, green hydrogen is not yet competitive with alternative fuels for many applications. Funding mechanisms, grants, and other financial support from central or regional governments will be critical in enabling the growth of the hydrogen economy. Lack of international standards and regulations. Unless international standards and regulations have been developed and harmonized, and a universally accepted certification system for green hydrogen has been implemented, there is the risk that hydrogen that is produced in one country will not be recognized as green in the imported country. Development of supply chain. There's only been a small number of international demonstration projects in Asia so far. While this demonstrated that small volumes of hydrogen could be produced and shipped, these transportation options are not commercially available yet, and more time will be required for full testing and rolling out those on a larger scale. Hydrogen is clearly on a pathway to decarbonization. There is a huge level of ambition among sponsors with large volumes of clean hydrogen capacity proposed, but few projects anywhere near over 100 megawatts, anywhere near to FID. There is a large interest in green hydrogen, with most based on the alkaline technology, but the supply chain is still lagging and with limited capacity. Electrolyzer costs are expected to fall as units scale up and the supply chain increases capacity and automates, and that's so that specific capex could halve by the 2030s. At best, green hydrogen may match blue hydrogen costs during the 2030s, and transporting hydrogen presents a challenge, especially with the shipping. So that concludes my presentation today. Thank you very much for your time today, and please do not hesitate to reach out to me to discuss about how Mott MacDonald may be able to support you with your own hydrogen